When forecasting convective weather, we're particularly interested in the ability to calculate buoyancy. In particular, we want to calculate the convective available potential energy, the energy that's available for convection. We start by asking how much kinetic energy does a parcel gain per unit mass in rising through a distance dz due to its buoyancy. Now the buoyancy equation, dw-dt, which is the acceleration of parcels of air in the vertical, is equal to g divided by TV, the virtual temperature in the environment, multiplied by the difference between the virtual temperature of a parcel of air and its environment. Remember that the virtual temperature takes into account both the parcel's temperature and its water content in terms of water vapor. The more water vapor it contains and the warmer it is, the more buoyant it is with respect to its environment. Now the buoyancy equation gives us acceleration, and acceleration is simply force per unit mass. So if we consider a mass of 1 kilogram, then the kinetic energy gained in moving a distance dz under the influence of that force is delta Ek is equal to F dz. And so the energy gained by a parcel of air per kilogram, delta E kinetic, is equal to G dz on TV multiplied by TV dashed minus TV. That equation is reproduced there in the box. What we want to do is to integrate this equation over height to get the total energy, the convective available potential energy. And we do this by replacing dz by dp. This is done firstly by writing down the hydrostatic equation shown there, dp naught dz is equal to minus rho naught g, and replacing rho using the ideal gas law, or the equation of state, P equals rho RD TV, which gives us the equation in the second line, dp naught dz is equal to minus gp on RD TV. We then rearrange that equation, multiply both sides by dz, and then multiply both sides by RD TV on gp, and obtain dz is equal to minus RD TV on g dp on p. And dp on p is d log p, which gives us that last expression. And so now we have a dz, we can substitute that back in the equation for kinetic energy and integrate that from the pressure of the level of free convection to the pressure of the equilibrium level. So there's our equation for delta Ek, and then we integrate that, shown there. So the CAPE is minus RD by the integral from pressure at the level of free convection to pressure at the equilibrium level of the difference between the virtual temperatures of the parcel and the environment by d log p. So what is this integral equal to? Or what's inside the integral equal to? Well, it is the area enclosed on a skew-t log p diagram by the environmental virtual temperature profile and the parcel virtual temperature profile, and that's shown schematically there. So the environment curve is the red curve, and the parcel curve is the yellow curve, and the enclosed area shown there in orange is the CAPE. Now typically on a skew-t log p what's plotted is temperatures, but you can calculate the virtual temperature from the temperature and the dew point profile and get the proper CAPE. If you calculate CAPE just using the temperatures, the value will be less than the actual value. So convective available potential energy, or CAPE, is the potential energy of a parcel that is available to be converted into kinetic energy as it rises due to buoyancy from that level of free convection all the way to the equilibrium level. So level of free convection parcels first become buoyant. At the equilibrium level they cease to be buoyant, although parcels of air can overshoot that level due to their momentum. The CAPE is directly related to updraft strength in convective clouds, and it's a very useful indicator of stability. The larger the CAPE, the more unstable the environment, and it's used in thunderstorm forecasting a great deal. Of course, we've assumed parcel theory in all of this, and parcel theory assumptions are only approximately met. So, for example, there's actually entrainment of environmental air into a convective bubble, and that will reduce its buoyancy. So if you're mixing with cooler air you reduce the virtual temperature, and if you mix with drier air, you also reduce the virtual temperature of the parcel, and hence the difference between the parcel virtual temperature and that of the environment, and therefore the CAPE. Precipitation loading is the effect of liquid water's weight upon a parcel's weight, and that also reduces the buoyancy. All these things given, we also need to look at the vertical distribution of CAPE and not simply its total value. CAPE concentrated lower down in the environment while parcels are still accelerating, so in other words a short and wide profile, may be more effective than the same CAPE that's distributed over a greater depth, tall and narrow, because of the effects of entrainment and precipitation loading.